basically what Catan talked about. It's border complexity. So a lot of the notions Catan already defined, I'm going to define them again because I think they're important. So I'm going to talk about depth 3 powering formulas, which for those of you at boot camp you saw, and I'm going to tell you again. I'm going to talk about the border complexity version of that, and then I'm going to give you a bunch of questions. Okay, so I'm going to try to concrete questions. We are in a concrete building, actually. So, yeah. But to some extent, there's not going to be any really results here. I'm just going to mostly highlight things I think are important and questions. Okay, so the definition of complexity I really want to focus on is this depth 3 powering formula. Oh, right, sorry. Okay, sorry. The theme of this lecture to some extent is the following. So in algebraic complexity, if we want to prove a lower bound, typically we would do something like the following. We say suppose that F has a small circuit, and maybe this is a small restricted circuit. What we end up doing is we come up with some sort of complexity measure, and we say that the complexity measure of F is small, for some definition of small. Okay? And then what we do is we find some hopefully explicit F naught, where the measure on F naught is large. Right? And then we do the natural thing is we conclude that F naught is hard for this restricted circuit class. Okay? I want to say, put this picture a little bit differently and say, well, this is an implication, and it's great for lower bounds, but I don't want to be heretical. I'm a complexity theorist, but I really want to ask about upper bounds. Right? Okay, so suppose that F is small. Does that mean that F is easy? Okay, this is the question. Okay, and I want to try to explain to you why this question is so mu is some sort of measure, which is as of right now not defined. But I'm going to make this concrete as the lecture goes on, and hopefully that'll become clear. But this is the broad type of question. Okay, so let's make concrete what mu will be and what the restricted circuit size will be. Okay, so I'm going to have a polynomial f of x, and I write this is a vector of n variables. So all my polynomials will be n variables, and they'll be degree at most d. I'm going to say this has a expression of the following form. So this is going to be a depth 3 circuit. There's going to be a sum gate at the top, sum gate at the bottom, and this is going to be a powering gate. It's sort of like the caret on your computer. This will be a degree d powering gate. Okay, and f has an expression of this form. If f of x is equal to, you have a summation gate. The fan in here is s, which is why this s is here. Then you have alpha I1 x1 plus dot 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 plus alpha in xn to the d. Okay, and so these alpha ij's will be in your field. And for the people who actually are paying attention, this is a homogeneous expression just to make things simple. Okay, so f is a degree d polynomial, and you want to express it as a sum of powers of linear forms. Okay. Sorry?
Do you also want coefficients outside the powering, or
so maybe, I don't know, f is a homogeneous, I don't know. Yeah, no, outside, you don't need coefficients here because you can always... Sure. Sure. We can do that. All right. Okay, great. Okay, so this is the model of circuit complexity in the sense that this is obviously an explicit expression saying that this is, a simple polynomial if s is small and d is small. Now I want to define my measure mu, which is also something we saw last week. Okay, so first I'm going to define in my own funky notation, this is going to be a set of polynomials. And what is this going to be? This is going to be the space of partial derivatives. Okay, so you're going to take your polynomial f, and you're going to take the following derivative, and this is the notation. In more familiar calculus notation, it's going to be the following. So you're going to differentiate x1 b1 times, and you differentiate xn bn times, and this is the differential with respect to f, and this is going to be just some exponentially large set of polynomials. Okay, but the point is that even though this is exponentially large, this is contained in the space of all polynomials, which is a vector space. Okay, and so you can measure the set not by its size but by its dimension. Right, so mu will be the dimension as an F vector space of the set of all derivatives. Okay? And just to remind you, there's some very basic lemmas that we have here, which, if you didn't see them last week, you can do at home. Right? Is that suppose that f has one of these expressions. Right? So it's a depth repowering formula, the top fan is s. Then that implies that mu of f is at most s times d plus 1. Okay? So this is saying that if f is easy, then the measure is small, which is exactly what I'm talking about here. Okay? And then, what's step 2 in this program? Right? Step 2 is find a polynomial which is large, has large measure, and we also saw this boot camp, right? That the measure of x1 up to xn is equal to 2 to the n. Or we saw that it was at least, but it's actually equal to. Okay? So that would imply that if you work this out, that s is at least, in this case, to the n over n plus 1, to compute this monomial, right? Because n here is going to be d, because this is homogeneous. Okay, great. Okay, so it seems like the story is done. I shouldn't have moved that down. Okay, good. Seems like the story is done, but it's done if you're a computer scientist. But if you talk to a mathematician, they say, well, what is the right answer? What is the truth? And because in some sense, they care about that. Okay. Okay, but so what is the truth? Okay, so well, we also saw last week the following, that x1.xn has some expression where s is at most 2 to the n. Okay, so this is like this Fisher formula. Okay, so that seems interesting. I mean, there's a 2 to the n upper bound, 2 to the n divided by minus 1, n plus 1 lower bound. It turns out that actually, if you stare at it for a long time, you can shave off a factor of 2. So this is sometimes known as the Glynn formula. Okay, so now we have these gaps, and what is the right answer? Okay, so the usual complexity theory way of doing these things is you take the best upper bound you assume that's tight, and that should be the bound, right? So it turns out that, but the question is, what is the truth, right? And there's this theorem of CCG, who are Carlini, Catala, Sono, Jeremita in 11, that actually proved that s is 2 to the n minus 1. Okay. Now, these are a bunch of math folks, and in computer science, you usually only use 2 years, and because it's always really clear what those 2 years should be. With math, it could be with math, it could be year 11, it could be 1711, 1811, 1911. In this case, it's actually 2011. Okay, so in that sense, it is a more recent thing, I think, but this could have been proven in 1911 probably. Okay, so basically, this is saying that we do have the right answer, actually, what this monomial is, and in some sense, I'm not. For me, this I think was good enough. Okay, so I should mention that if you push these techniques, you can actually get that s is at least 2 to the n divided by it's omega 2 to the n square root n. Okay, so you can improve a factor of square root n just using a refined version of this measure. Okay, so for me, this is basically a good enough lower bound. Although this is still interesting, but the question is why is this interesting from a computer science point of view? Right? Obviously, you're getting the exact answer, but the real reason is that that this is interesting is that this is not proven using a complexity measure. Okay, and so basically, complexity measures are all, it's bread and butter of the people in this room, and so to say that this is not proven using this idea is somehow very interesting. Okay, so in some sense, it's not necessarily the answer that's interesting, but the techniques that are going involved. And so I want to explain to you the subtleties of I'm not going to actually prove this for you, but subtleties of going into this picture. So, okay, so the main example I want to talk about, so Catan had an example about border complexity with 8 variables, I don't know, something. I want to give you an example of border complexity with 2 variables. Okay, so let's see this. Let's consider the polynomial x to the n times y. Okay, and I want to express it as an expression of this form where d is 2. no, sorry, d is n plus 1 because this is an n plus 1 degree polynomial. Okay, so what can S be in this case? Well, if you do some variant of the Fisher formula, you can get that S is at most n plus 1. Maybe n. I don't know. There's a plus 1, maybe. I don't remember. Okay, and then, right, if you use this, yeah, I think it should be n. Okay, so the upper bound is sort of some Fisher thing, and there's a lower bound of n via this CCG thing. Okay, but if you use the measure is going to say that S is at least 2. So this is a concrete example where the measure actually, like, no matter, like, even this sharper variant of this measure cannot prove the optimal lower bound here. Okay, so there is some gap, and now I want to explain to you why this is a gap with the explicit example. Okay. Okay, so okay, it's like some video game that I'm losing. Okay, okay, let's consider the following expression. Right, you take x plus epsilon y to the n plus 1. Okay, so epsilon, think of it as small, is the sort of the usual game here. Okay, so what's going to happen when you express this out? You're certainly going to n x to the n plus 1 plus epsilon n plus 1 x to the n y plus, you know, things which are smaller than epsilon squared, right? So if you then subtract, right, so what do we want to compute? We want to compute this thing, but this is really annoying. Okay, so let's subtract out x to the n plus 1, and then let's take this whole thing and divide by 1 over epsilon n plus 1. Right, and what did we get? We got x to the n y plus something which is little o of epsilon. Right? Big O of epsilon, yes, thank you. Okay, so what is this really saying? So what happens when we take epsilon going to 0? Right, when we take epsilon going to 0, so let's work over the complex numbers for now. If we work over epsilon going to 0, right, this thing is going to become negligible, right? So in some, you know, say Euclidean topology, what's going to happen is that x to the n times y is in the limit of top fan n2. All right, so this is sums of powers of sums of powers of linear forms. Top fan n is 2. We take limits, so we're going to have an epsilon term here. We take epsilon going to 0, and we get what we want. Okay, so this is going to what Katan was talking about in terms of infinite approximation. That here we have this monomial, right? To compute it exactly in this model requires size n, but you can approximate it infinitely by size 2. Okay, so this is not dramatic in the sense that it's still a polynomial factor in the degree of your polynomial, but the point is that there's the concern, which is what, you know, Katan was talking about in terms of this border, that maybe bigger gaps could happen, right? And so that's what we want to understand. Okay. Cool.
But here bigger gaps will not occur, right?
Can you prove it?
Oh no, this is for what? Unrestricted depth, is it?
Depth 3 powering. So I would not, I mean, I'll get to this later. I don't think big gaps should occur here, but I can't prove it.
No,
And I don't know anyone else who can. So, okay. So one thing that's worth noting, yeah.
What's a big gap? I mean, do you want this model to be closed, or is it just that you want the thing to have a polynomial size circuit?
Right, okay. So,
But here you also divided by epsilon, right?
yeah, so, okay. I'll get to all these things in my talk. And I could answer them now, but then it would ruin my notes. So, okay, so the first observation is what Nitin was just asking about. Okay, you're taking epsilon going to 0, and what does that do in this expression? So let's parentheses here. Okay, so the point is that we divided by epsilon here. So this is a valid expression whenever epsilon is not 0, right? Because we're dividing by epsilon. So the observation is that the coefficients, I can spell. Okay, coefficients are going to infinity as epsilon is going to 0. Okay, so this is over the real numbers, right? So what this is saying is that the reason you can't take limits inside of the computation is because the coefficients go to infinity. But the point is that somehow, magically, when you put all the coefficients together, you get something which has bounded coefficients. So there's something, I mean, in some sense, all of algebraic complexity is about understanding massive cancellation. right? That we have a bunch of things, we want to understand, you add them, for example, and how does that transform the situation? And this is an example of massive cancellation in some sense, okay? And so that's why we have to do something to understand it. Okay, so this is an example of what it means to have an infinite approximation, but now let me give you a more general definition which captures the border or the closure of depth 3 powering formulas. Okay. Okay, so let's say that f of x, again, is n variate and say homogeneous of degree d, I guess, is in the border of this class. If what? Well, what are the salient features of this expression? Okay, so you have to make a decision to some extent. Do you want to work over characteristic 0 or not, in the sense that do you want to use your Euclidean topology? I'm going to give sort of a formal definition which will work over any field. To actually show that it agrees with the Euclidean topology takes someone else, because I don't know how to do it. Okay, but here's the definition. What we want to do is we want to say that f of x is equal to what? Well, it's going to be, again, a sum of powers of linear forms. And it's going to be the same thing I wrote over there. That's a 1. You have alpha. It's going to be an alpha I n xn, and you have, say, d, for example. But there's going to be a couple changes, okay? One is that I'm going to allow my alpha ij's to be power series in epsilon, okay? So they're no longer going to be, just things from your field. They can be power series. So these are just, formal linear combinations of epsilon, where we're thinking sort of epsilon is small, so epsilon squared is smaller, right? And these are a priori infinite objects, okay? They're infinite power series, but they're formal. Okay, so there's no issues of like convergence or something. Okay, so we have, this is over the power series. Okay, then what we're going to do is we're going to take a division by 1 over epsilon to the n. Okay, and then it's not going to necessarily equal f, but it's going to equal something. It's going to be f plus big O of epsilon. Okay, so the point is that even though we're the claim is that even though we're dividing by a big power of epsilon, we get a constant term which does not depend on epsilon, and this thing is O of epsilon. So there's no, so even though we're dividing by epsilon, it somehow magically cancels, and we get something which is only depending on polynomial, yeah, okay, you get the idea. Okay.
Why would you use power series now? Isn't it kind of the answer to be homogeneous? Because the rest is just going to be very high powers of epsilon. They were just
Patience. Yeah. I will get to that. Okay. Yeah. So the salient feature here, though, is that n is going to be called the order of approximation. Okay. And so a priori, I've not actually bounded n in any way. Right? So there's n variables, it's degree d, there's size s, but I've not bounded n in any way. It could be a priori unbounded in any way. So there's like this is why it's capital. Right? Okay. So the fact here. So this is the definition of the border of depth 3 powering formulas. These are called depth 3 powering formulas. And the fact here is that this definition I gave is equal to the limit, this closer thing, is the limit of under epsilon goes to 0 of depth 3 powering formulas when you have this epsilon in some precise sense. Okay, so it's basically saying that you look at this class and you basically, is that what I meant? Well, sort of, yeah, but basically anything that can be infinitely approximated over here can be expressed in this way. Right? And it's clear that these things can be infinitely approximate because obviously if you just set this, take epsilon to go to 0, this goes to 0 also. Okay. 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 What I now want to show is to understand how does this measure interact with taking this closure. Okay, we defined a measure which is small on the actual computation. It's over here. We want to say it's also small on the border. Okay. This is more challenging. Okay. Yes. Okay, so the lemma here is that suppose that you have something in the border. We want to say that this implies that the measure of f is still at most s times d plus 1, which is the same thing it was as before. Okay, so taking this closure doesn't do anything to the measure. Okay, so how does the proof go? Right, well, we have that f of x plus some one of these terms is equal to the summation of some linear forms here, right? And there's some epsilons floating around. Okay, and right, there's a 1 over epsilon to the n. Okay, but the point here is that, okay, I guess I'm to some extent assuming this is algebraically closed. Point is that if you just look at this expression, you can interpret this over the Laurent field. Okay, in the sense that when I defined my class over here, I said these are power series. Okay, power series are not actually a field. Okay, but you can take, you know, it's a ring, right? So then you can take the fraction field. The fraction field is the Laurent field. So what is the Laurent field? The Laurent field, these are just things where you have some combination, linear combination, where it's at most, you start at minus m. So power series is where you have things that's, you know, you have the constant term, things, coefficient of epsilon squared. Here you're allowed negative powers, but only a finite number of them. Okay, so you have something, you know, beta I epsilon to the I, where I starts at some, you know, finite negative number. Okay, and the thing is that Laurent series are a field. So this entire expression you can view in this field, right? And because, you know, the way this measure was defined, this measure it doesn't really matter what field you're going over. So you can treat this as some computation in this bigger field, and what you end up getting is that the measure, so let's call this thing here f of epsilon. Okay, the measure of f of epsilon is at most s times d plus 1. Okay, so what that's really saying is that if you look at the dimension over the Laurent field of these partial derivatives of f of epsilon, right, this is at most this thing. Okay, but now I want to stare at what does this mean. Okay, as Ramprasad said, it's sort of in the boot camp. Let's look at, okay, so I usually think of these terms in terms of vector spaces and so on, but it's really helpful to look in terms of ranks of matrices, right? So what is this thing looking like? Right, these are a bunch of vectors, right? Let's assemble them into a matrix, okay? So what are the rows indexed by? The rows are indexed by, you take some derivative, right? You take some derivative, that's how you got this set here. How are you indexing the columns? Well, this is going to be you index them by monomials, okay? And what you put here, is you put in the whatever coefficient is supposed to be, right? Okay, so you take a bunch of these things here, you assemble them into a matrix. What this dimension is saying is that if you look at this matrix, it has low rank over the Laurent field. Okay, but now let's say, well, what's actually in here? Well, you have entries in the Laurent field, right? Which is not necessarily the original field you started with, which is where this statement is lying. Okay. But what we want to do is we want to say, what happens when we take f itself and assemble the same matrix? Okay, so let's call this matrix here m of f sub epsilon. Okay, so following Ramprasad's notation. The claim is that if you take m of f sub epsilon and you let epsilon go to 0, this is equal to m sub f. Okay, and why is that true? It's because of this thing, right? That this expression, at least if you work over your characteristics of knowledge, this is some expression, right? You just let epsilon go to 0. Okay, maybe the coefficients blow up, but you never actually reach 0. This thing itself goes to 0. So the limit of the matrices as epsilon goes to 0 is just m sub f, right? Okay. Now the rank. So because of the Right, so this is saying that then you have the rank over the Laurent series of m, this thing is at most s times d plus 1. But what is rank? Right, rank is saying that, well, okay, it's rank, but rank is characterized by saying that certain determinants are 0. Right, so this equation is the same thing as saying that certain determinants are 0. Right, basically saying if you look at any large enough minor in this matrix, that determinant is 0, determinant of that submatrix. But the point is that a determinant is a polynomial, right? And saying that something is 0 should certainly still be true when you let epsilon go to 0. Okay, Right? Another way of saying is that, determinant is a polynomial. Polynomials are continuous. Things that are continuous are closed under limits. Okay, so what this is saying is then that the rank of f over your original field of m sub f is also at most s times d plus 1. Right, and that's what we wanted to show. Okay, so this is like the hardest thing I'm going to do here. So hopefully there are no questions, but if there are, even better. Okay. Claim it, like this claim? Like you take f sub epsilon. Okay, so this is the matrix associated with the partial derivatives of f sub epsilon. Okay, and if you look at this matrix, you get a bunch of things, and they're Laurent things in epsilon. Okay, but the point is that, and what we want to do is we want to take epsilon going to 0. Now this wouldn't be valid if you had an expression like 1 over epsilon. But the point is that f sub epsilon is a polynomial, and we know it's of the form f plus O of epsilon. So in this expression, you can take epsilon going to 0. Okay, and so what that's saying is that that's limit-wise. You take every entry in this matrix, you just set it, you push it to 0. Okay, and what this is saying, what this is saying here is that basically for every value of epsilon which is not 0, the determinant is 0. But the determinant's a polynomial. So if you have a polynomial which you know is 0 everywhere except at one point, it must also be 0 on that point. Okay, right, so this is saying that if you actually instantiate f in your field except at 0, then the rank over f of m sub f of epsilon is at most s d plus 1. That's another way of saying this. Right, the thing is that you can't actually set epsilon to 0 because this polynomial does not make sense when you set epsilon to 0.
This argument does not use L to the D.
Sorry?
So this argument is not dependent on the
No.
L to the D structure.
No. This is I'm being very concrete. So I'm trying to use an example. This is not at all dependent on any circuit structure of this thing. I'm just using this as a prototypical example.
Even the rank wouldn't change if you introduce epsilon in general for a polynomial.
Yeah. Yeah. That's right. Okay. Okay. So this is the proof of the claim. Basically saying that by passing the border rank, any sort of complexity measure argument you have should not, the complexity will never go up. Yeah, so okay. Yeah. That's basically, yeah, but the point is that complexity measures basically are rank based more of the time. Okay. Okay, so what is the punchline of all of this? Let's go back to this example, right? In this example, we have this tight understanding based on Fisher and CCG. Right? The measure thing doesn't give us a tight example, but basically what this is saying is that because there is an upper bound of 2, is that like complexity measures, ones that are, say, things that are defined by ranks of matrices and so on, these cannot give us an optimal lower bound. Okay. So we have an optimal lower bound, and I told you that it didn't use a complexity measure, and the point is that there's a good reason for that. It cannot, because there are good upper bounds in another computational model. Okay? Okay. So here's the first open question. Okay, so that's saying there is something to learn from things that are beyond complexity measures. It's not clear to what extent we're getting power. And we do have basically an optimal understanding of depth repowering because of CCG. But the thing we don't understand is what is, if you look at the monomial, right, this lower bound gives you a lower bound for S. But it's not just a lower bound in depth repowering, it's a lower bound for the border of depth repowering. right? And so the open question is, what is an optimal algorithm for the monomial in terms of the border of depth 3 powering? Right, so without the border, we understand what the right thing is, but what is the optimal algorithm here? And this is generally an open question. Okay, and it's not to say that resolving this would get you a Gödel prize, right? But I think there's an interesting question there because a lot of the techniques we're familiar with don't seem to resolve this. Okay.
So in general, you're saying as well, given the conjecture that Mulmuley said, that the closure of VP is not containing VP, that we cannot expect that rank-based approaches would work to separate VP even from the closure.
No, I mean it's still you cannot separate VP and VP bar using rank-based methods, which is basically what this punchline is saying.
Right. Okay.
Okay, but it's still conceivable that you could separate VP bar from the permanent using rank-based methods.
Not if VP bar is contained in VNP, like as another conjecture that he said, right?
No, that
That is open.
That is open.
well, no. If VP bar is in VNP, that doesn't say anything about the permanent being in VP bar.
Like permanent was in VP bar.
No, that is
Then there is a significant.
If permanent is in VP bar, that would suck.
Oh, I see. You're saying that, like, okay.
Okay.
So Mike,
Yeah.
is 2 to the n minus 1 not tight for the border complexity?
No, so we don't know.
We don't know that. I mean, we don't know. Do we know that you can do better than 2 to the n minus 1? As an
No.
algorithm?
I see. But you
So Christian, one sec. I've talked to mathematicians about this. Okay, so let me mention first of all. So I define this. This model of computation is also called Waring rank. Okay, so people are familiar with things like matrix rank and tensor rank. This is called Waring rank. It's been studied since the mid 1800s. Okay, and so this has like a lot of mathematical history. This is sometimes called the secant variety to the Veronese embedding. There's lots of names here. And the thing, it's very well studied, but as far as I understand, I've talked to mathematicians about this. I'm not going to say I understand everything, but there are no better upper bounds for the border rank of the monomial.
it's optimal S for the monomial there, right? The algorithm.
So this is an optimal, just non-border algorithm. We don't know better border algorithms for the monomial.
Border within like S.
Sorry.
You mean finding the smallest S.
Yes, understand the exact S, and there might be slightly better lower bounds. I don't think that to be true, but
What is this theorem then? Is greater than 2 to the n minus
that says that if you express,
Without the border.
this is without the border.
Don't close.
in the upper.
This is asking, what is the border complexity of the monomial?
Oh, that is without the border.
This is without the border,
Yeah, yeah.
But why are you using the same S everywhere now?
because it's the same S. There's just a bar. It's a bar or no bar.
So without the border, we understand this completely. With the border, there is a square root and gap.
Right.
Right.
Yes. Right. Is-
The first 5 cases, they indicate that the border complexity is exactly the same as the complexity. It's the 2 to the n minus 1. It was computed by Luke Erding.
So this guy Luke Oding has done a lot of computational experiments, and has proven and the suspicion is that this upper bound is tight, and that they've numerically verified this for the first cases. Okay. Any other questions before I go on?
So they verified for how many volumes?
5.
Wait, so what did they verify? Say again.
Okay. You want the monomial, and you want to know what's the smallest s for which this works. Okay, so they said let's do it on 5 variables,
Oh,
and 4 variables, and 3, and 2,
it's 2 to 10.
and 1.
It's either n square or 2 to the
Right. Okay.
But that's and they confirm this bound, the 2 to 10 minus 1. Sorry.
Yes, 2 to the n minus 1. Right. Okay. Okay. So the main question here, to be a little bit glib about it, is so basically is what is the power of epsilon? the main question is it an epsilon of power or not? Yeah. Okay. Okay, so this is the very specific concrete instantiation of border rank. And but I now just want to take a step back and just remind you of what Catan told us in the morning in terms of things like VP and VP bar. Okay, so what is VP bar? Okay, I'm not actually going to really tell you, but the point is that now you do the following. You define something called a universal circuit, which Amir alluded to in the boot camp. And what is this thing? This is a map that takes you from the field with S elements and maps you to n plus d choose d. So I guess I'm losing homogeneity here. And this is a map, which is a polynomial map. So every coordinate in this map is a polynomial. And the way you think about this is you're taking the data, based on where, the values of the circuits on the leaves and so on, and it's giving you the list of coefficients defining your polynomial. Okay, so this is the coefficient vector. Okay, and just as a small example, which I think Ramprasad did, is you consider the following. Suppose that this is your universal circuit. Okay, so you have two polynomials, x and y. Okay, two variables, and then you multiply x plus alpha times y plus beta. So alpha and beta are your constants, and what do you end up getting? Well, you get xy plus alpha y plus beta x plus alpha beta. Okay, and your coefficient vector then is 1 alpha y alpha beta alpha beta. Okay, so this is it's not a universal circuit obviously, but it's a universe. It's some sort of polynomial map that gives you something, right? And sort of what is a complexity measure really doing? Right here is it gave you a bunch of vectors, and you assemble the vectors into a matrix, and then you look at determinants of this matrix. The point is that determinants are a polynomial in the entries of this matrix, but the entries of this matrix depend on the coefficients of your f. So what you really get is you get a polynomial in the coefficients of f, which is 0 if f is simple. So let's see that in this example. Right, if you take these coefficients and you assemble them in a matrix like this, you get 1 alpha beta alpha beta. Right? These are the coefficients of your polynomial. Right? This is a determinant 0. Right? You get 0. Okay? And so what's the general setup for a lower bound technique is you want to find a polynomial p. And how many variables is this polynomial going to be on? It's going to be in the coefficients of your output thing. Right? So it's going to be on n plus d choose d variables, right? And you want that p composed with your map, this is big phi of s. Big phi of s is identically 0 as a polynomial, right? Because that's what's happening here. That's what happened in the depth repowering case, that you have some polynomial like the determinant, which vanishes on the output coefficients of your polynomial vector, okay? Okay, so what this is saying is that any lower bound technique that I know how to do, aside from CCG, basically gives you a polynomial that vanishes on the output of this universal circuit. Okay, and so basically, I'm not going to define VP bar, but basically you can do the same thing with VP where you place all the constants with Laurent series and power series you divide by epsilon n and so on, as I did over there. And basically the fact here, in the same way that what happens here, is suppose that you have f, which I'm now thinking as, this is a polynomial, and it's a coefficient vector, right? Suppose that you have p, which vanishes on the image of size s circuits. Okay, so I guess I didn't really need this, but what this is saying is that p will also vanish on the border, on the closure of this thing. Right? It's the same proof. Okay. So there's some, you can talk about the Zariski closure and algebraic geometry and so on. I kind of wanted to avoid doing that. But the point here is that any proof of this form it automatically says not just size but border size. Okay. Yeah, and so this is just to remind you what happened in the morning. And so this is basically the setup. And now I want to talk to you, I guess, about. I have 7 minutes, right? Yeah. Okay. 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 So this is the setup. I mean, I talked about the specific case of depth repowering and the general case about VP and VP bar like 2 minutes ago. But now I really want to get to questions because in a certain sense, I think there's a lot of accessible questions here, and I want to tell them to you so that you can solve them. Okay. So just to recall, this what I already wrote here is that if f has a small some power some expression, right? This gives us that f has a small border rank expression, just sort of by definition, which then gives us that f has a small mu. Okay. And in the morning, Catan was posing this question. Is VP VP versus VP bar? Okay. I can admit to you that when I first saw this question, I said clearly they're equal. Then I said clearly they're not equal, and now I don't know. But the point is that to some extent, at least following existing tradition, if you want to attack this question, there's some idea that you should at least look at restricted cases first. Okay. And so I want to tell you about these restricted cases. And the restricted case I want to tell you about is this case. Right? So the question here is, can we do the converse to this chain of expressions? Right? What would that mean? Suppose I give you an f and it has a small mu. Does that imply it has small border rank? Does that imply it has a small actual expression? Right? In particular, if you, like I did some time ago, believe that VP equals VP bar, then it better be the case that at least you can go from here to here. Right? Well, it better be the case that if you're here, you better be in VP. So I want to prove that to you. Okay, so suppose, in fact, that f has a small measure mu. Okay? I want to prove to you that f is in VP. So mu is the same mu that I had before. I'm going to have one mu here. Yeah. Okay. I'm actually going to prove something stronger, which is that f has a small read once algebraic branching program in every order. But I'm not going to talk about that. Okay. So what is the proof here? Well, in some sense, I'm going to be cheating because I'm going to punt it to Noam Nissan. But basically, what you do is the following. So step one, suppose that f has a small mu. Right. So this is some measure. Then you can show that f has a small rank partial derivative matrix. Okay, so the partial derivative matrix is some other complexity measure that Ramprasad defined last week, but I'm not going to define for you now. It's some other complexity measure, and you can show that if mu is small, then this rank is small. Okay? And the second step is what Nissan showed, is that, implicitly at least, if you have this, then you have a small read-once ABP. Okay, so Amir asked this morning, what are restricted classes that are closed under taking limits? Okay, and so read-once ABPs are an example of this. So the way I stated it, it's not super obvious, but what you can actually show is that the fact here is that with W, read-once ABPs are equal to the with W, the closure of with W read-once ABPs. Okay, so there's actually no loss in parameters, I think. So what we've done is we've done something sort of silly, which is that, sorry? So I haven't defined it for you. We can do it offline. But the point is that this class is closed under taking limits. Depth repowering is contained in this more robust class. And this robust class is closed, so depth repowering is clearly in VP. Okay, so this is something I think, the only example I know where yes, depth repowering, the closure of that is in VP. So depth 3 powering is very weak, right? It's not general depth 3.
Is that diagonal depth 3?
Yes, this is diagonal depth 3.
Or that is your notation for diagonal depth? That is closure is in VP, that's okay.
That's right. Yeah, that's right.
And where is the proof now?
Okay, so I didn't really go through it too much, but basically there are two steps. One is that you convert from this mu measure to this partial derivative matrix measure. That you say that if this is small, this measure is small. Nissan was able to show that this measure exactly characterizes the width of Riemann ABPs. And what that in particular shows you is that Riemann ABPs are closed. Like Riemann ABPs equal their closure. Okay? And they're also contained in VP. No. This is this particular measure which I just erased, but it's this partial derivative measure. Yeah. Okay.
And if you take away that width W thing, is arrow APP closed under bar operation?
I mean, this holds for any W.
I don't know what is width W. I don't know.
Like there's a parameter of size. Width is the size parameter. So small size Riemann ABPs are closed. Okay. Okay. But the open question here is this says that, this is in small Riemann ABPs and small VP, but the question is, how do these two classes relate? Right? That's what we don't know. So, if you take depth 3 powering and you put its closure, is this contained in small depth 3 powering? Or we don't know the answer to this question. Oh. Yeah, with polynomial load. So small and small, whatever small means. Okay, so now this goes back to Christian's question from some time ago, which is that, the next topic. You look at this thing, okay, there are power series here, okay, and then there's order of approximation, and Christian was saying that actually you don't really need power series, you only need finite series. And that's true, and that goes into the following proof of what I want to say next, which is that suppose that you have you have f of x.
Do we know anything on the bound of the S and S prime for like the bar here? This open question they have. There's an S here, like sigma S.
Everything I know I told you.
No, but what is S and S prime? There's nothing.
Polynomial relation.
But
Just
we don't even know some explanation. That's my question. Like some.
no.
No.
Everything I told you, everything I know, I told you. Okay. So we have a border expression of the following form, right? And we have all these power series. Okay. And then the claim here is that suppose we want to actually compute f. Then the size of f in like the VP sense or something is at most polynomial in the size of f epsilon, so the expression that the computation you're doing in the Ross series, the degree of f, and n, the order of approximation. Okay, so what this is saying is that you have this order of approximation factor, and if the order of approximation is very, very small, like polynomial, then you actually get a small expression for f itself. So the only way that you can have things out, in the border, not in VP, is when the order of approximation is really, really large. Okay, and so what's the proof of this? The proof is interpolation. And since I'm running out of time, I'll just sketch it. The idea is that you look at this expression, and you have these infinite power series. And the observation is basically you can truncate them at some point, and it doesn't really mess up too much. Okay? And then you just have this epsilon you need to deal with. And if you rearrange this expression, you get epsilon to the n like this. Right, so I've just multiplied the entire thing by epsilon to the n. So it's saying that if you look at this expression, this is now a polynomial in epsilon, because I discarded many, many high terms. This is saying that, yes. Right. This is saying that if you look at the coefficient of epsilon to the n in this expression, it's f. And so what you do is you just interpolate that out, right? You do a brute force interpolation, which is why you're paying all these things. And this is a univariate thing. And then you can extract this coefficient, and that's how you compute f. Okay. So if the order of approximation is small, then you're golden. Okay. So what do we know about the order of approximation? Because as of right now, I just told you this is not bounded, right? So that seems really bad, right? It could be bajillions. Okay, so here's the following theorem. This is due to Lechman and Lichtig in '89, and also Bergesser in '01, is that for a border size S computation, you can basically, without loss of generality, take n to be at most exponential in S. Okay, so you could have computations where n as an order of approximation is really, really large, but they're saying if you're in small border complexity, then the order of approximation is at most exponential in the size of your circuit. Now, the size could itself be exponential, in which case it would be doubly exponential. But this is saying that there is a bound, a finite bound, okay? And so,
Is it some sort of Cauchy logarithm?
at some point you use Bazoo. What you do is you set up a system of equations, and you need to like avoid a bunch of stuff. Sorry. Yeah. Okay. But okay. Okay. So this is saying there is a large, there is some bound, but to get a simulation result, we need a polynomial bound. Okay. And that's obviously a big difference. So the question is, what happens if n is super polynomial? What can we do there? And I want to say that any algorithms here that you could possibly develop require massive cancellation. So what do I mean by that? Right? Look at this expression. Right? This is saying that epsilon to the n times f of x is equal to something here. Okay? But this is saying that if you do all of this stuff, the leading term in epsilon is epsilon to the n, and n is super polynomial. And somehow, how can you get something epsilon to the n which is super polynomial? Well, if you involve, just an epsilon to the million times x1, certainly you get a larger order of epsilon. But but if you sort of don't use high powers of epsilon, it seems very hard to arrange for all of the low order terms in epsilon to massively just disappear. So somehow it says that to use this effectively, you require massive cancellation, which seems like very, very weird. And so the concrete question, is, okay, can you get algorithms for this?
And
Even
also to get that massive cancellation, you really need that this coefficient in that symbolic determinant, the extension, they would have to lie in an extension field that is very high. Otherwise, you won't. That is my intuition.
sorry,
To get this kind of massive cancellation,
you need an extension field.
of exponential size.
What if you're over the complex numbers? I don't like. How are you extending things? Let's work over the complex numbers. Okay. So this is okay. So what I told you so far, if you have a low order approximation, you can do this simulation. But we already know, because of this claim, yes, this one, that border rank of depth repowering is actually in VP. Okay. So the concrete question is what is the order of approximation for depth repowering in the border rank? Okay. We know there's some bound, but maybe you could show that depth repowering is such a weak model of computation, it cannot arrange for this massive cancellation, right? Like there's some concrete ways that I know how to show that massive cancellation cannot happen using structural results I actually showed in the boot camp. But in general, it feels like this is too weak to have this massive cancellation. So it seems like you could possibly rule that out, and that would give you another proof of this fact. And it would prove this open question, right? If you could show the open question, if you could show.
So this doesn't come out of that?
Not to my knowledge. Yeah, right. Right. You might lose some parameters, but you might say that they're equal. Okay. Cool. So.
Show that the border of sigma by sigma power sigma is a slightly larger sigma power sigma.
So I don't understand. What is that notation? Small, slightly larger?
No, it's a depth-free diagonal circuit. If you start off with, if this were true, if you start off with
Here, but right now, what is it?
that's a depth-free diagonal circuit.
It's some model of computation, and what this would say is that if you could show the order approximation is low, then this model is closed under taking limits if you allow yourself to lose some in parameters.
But right now, what do we know?
In terms of this, we know nothing. I mean, I told you everything I know. We have n is at most exponential, and you know, it seems like, you know, some of the techniques that we have for this could rule out massive cancellation, but, you know, we don't know. Okay, so I just want to take 2 more minutes. You can see I only have a little bit left. And tell you about polynomial identity testing. So I'm just going to remind you what a hitting set is. Okay, so you have some class of polynomials, some set C of n-variate degree D polynomials. Okay, so this degree at most D. And this has a hitting, and H is going to be a subset of n tuples. It will be a hitting set for C if what? If for all f in C, you have that f is identically 0, if and only if f is 0 when you evaluate on H. Okay, so f being 0 is identically as a polynomial, and being 0 on H is an evaluation statement. You evaluate on every point in H, and it's always 0. Okay, so we know how to construct small hitting sets in you know, for various classes like depth repowering. But the observation here is that suppose that you have H as a hitting set for C. Okay. The point is that this does not imply that H is a hitting set for C bar. Okay. So as Catan was basically saying this morning, everything from algebraic geometry, if it works for C, it works for C bar. So this is saying that we can do things algebraic geometry. I mean, I'm being glib, but like this is saying that this is not an algebraic statement or algebraic geometric statement. That like it works for C, it does not necessarily work for C bar. Okay, and why is this true? Well, if you have f of h, so you have some f of epsilon which converges to f as epsilon goes to 0. Well, you take f of epsilon, you evaluate on h. These are simple. You know this is non-zero, right? And what you want to do is you want to ask, well, does this mean that f on h is non-zero? Right, the answer is no, because if you take something non-zero and you set epsilon to go to and you take epsilon to 0, it could be that, you know, many non-zero things converge to 0. And you can actually find examples where this happens. So it's not to say that just the proof technique breaks down, but actually provably hitting sets for C do not necessarily extend to the C bar. Okay? Okay, that's observation number 1. What's observation 2 is that basically every polynomial identity testing I've ever been involved with, if it works for C, it works for C bar. Okay, so this is, and in some sense this is the same reason, is because all the lower bounds we know how to prove, aside from, say, the CCG lower bound. If it works for C, it works for C bar. Okay, so this is sort of a strange state of affairs. And here's a less concrete question, is basically, can we understand the difficulty in general of PIT for C versus C bar? Okay, so that's not very concrete, but anyways. Okay, so I think this is all I want to talk about, and there are many vague things, but please ask concrete questions.